Bonjour? Pourquoi? Oh, yeah, sorry. Huh? Ah, you got a Evan bromance going on? Ah, huh? Ah, got it. Which one? Oh, yes, Caesar. So, how are we doing this morning? Tired? Fatigué? Pourquoi? Pourquoi vous êtes fatigué? Beaucoup de travail de maison? Huh? Uh, yeah. An examen de chinois, n'est-ce pas? Yeah. All right, well, let's get to it. So, last time we were working on floating point stuff, so we want to continue with that. And if I can find them, I do have some notes on this that I want to post once I remember where I put them. Okay, anyway, so let's just take an example of a number and start to work on the encoding process. Okay, so we'll do this in a couple of stages, by which I mean that we'll still use like the digits 2, 3, 4, etc. to start with, and then we'll kind of eventually get it so that it's only all in binary. And again, for sake of demonstration, we're going to do this all in just 8 bits. 16 and 32 bits and whatnot work basically the same way with a few minor tweaks that we'll see, we'll talk about in a minute. Okay, so let's take the number 2.5. Okay, and like we did with the integers where we talked about int8 or uint8 or something like that, I'll call this data type a float 8. It's a floating point number, and we're doing things in 8 bits, so hence the name. Okay, so the first step that would help if I could spell this morning. Scientific notation. Okay, but when we do that, we're going to write it in sort of binary scientific notation, not base 10 scientific notation. Okay, so how do I write 2 in binary? Okay, well, first off, it depends on how many bits we're going to use, right? So for this step, let me not worry about how many bits we're going to use. Let me just write it down, and then we'll fit it into a specific number of bits in a minute, okay? So I would write down 2 would be this, right? 1, 0, because you have, and in fact, let me actually write it this way for let me write it like that. Okay, so the 2, the 1, the 1/2, the 1/4, those are the place values. Okay, and this is sort of what we talked about right at the end last time, that if we're counting up integers, so whole number part, right, we have the ones place, then the twos place, then the fours place, eights place, and so on. Okay, so we just use whatever places we need to. And then if you move to the right of the radix, then instead of it being powers of 2 that are positive powers, it's going to be negative powers of 2. So you'll have 2 to the minus first, which is a half, 2 to the minus second, which is a quarter, 2 to the minus third would be an eighth, and so on. Okay, is that all right? Okay, so so right now I'm just writing this in binary, like on paper. It's not necessarily what we're going to shove into the computer. But this will be sort of the first step along the way. Okay, so for 2, well, we've got a 2. We don't have any 1s. And so that's it for the whole number side of it, the stuff to the left of the radix. Okay, and then the stuff to the right of the radix, well, I picked a half just for cleanliness, so we'll have this, and that's it. Okay, good. So that is our binary fraction. Okay, so I'll write here a subscript of the word 2 to indicate that we're writing things in base 2, not base 10. Okay, so that's how I know that that's 2.5 and not 10.1. Okay, yeah. Okay, so is that part okay? Yeah, so we just wrote down a number. Keston, yeah. Uh, okay, the fact that it's in the middle is is not really relevant. It's just I didn't write like 4, 8, 16 and stuff because I knew we didn't need them. Okay. Um, so maybe the better way to answer that is that the radix is always between the 1 and the 1/2, right? In the same way that in base 10, it's always between the ones place and the tenths place. Okay, so the fact that it's sort of geometrically in the middle on the way I wrote it is just because of the number I picked. But if I pick something like 2 billion point 5, then obviously I would need a lot more places. Okay. Yeah, so there's nothing special about the fact that it's in the center on the screen. It's just that it's between the ones place and the halves place, and it will always be there. Okay. To start with. Okay, now to write this in scientific notation, what are the rules about scientific notation? Yeah, the radix is exactly one place to the right of a single digit, and then that digit is always a 1. Okay, so the first thing I'm going to do is I'm going to shift this like so. Okay, and I'm here. This may be a little confusing because I'm mixing binary stuff and base 10 stuff because I've written the digit 2 here. Okay, but don't worry, we'll binarize this stuff here in a moment. Okay, so all I did was I took the bit pattern 101, which is what I had up above, right? And I shifted everything, or equivalently moved the radix, so that it was 1 point and then some stuff. Okay, and the reason that we want to do it that way is just like in regular scientific notation, you would write 6.022, not 60.0 or 0.22 or anything else, right? So what did we call numbers that were in this form, where it was exactly one digit or bit in this case before the radix? We called them numbers that are in this form. Normal, normalized, okay? And numbers that are not in that form are therefore not normal or denormal, okay? Okay, so good. Now that we've got that, we need to do 3 things, okay? We need to encode the sign, the exponent, and the mantissa, okay? I don't have to encode the base, which in this case is the 2, because we're always doing this in binary, so we don't have to specify that all the time, right? That's sort of just a common assumption. However, the sign, the exponent, there he is, inf, it's a preposition, it's a slang preposition with a verb that's gotten condensed into a single letter, right? What's up became sup. Okay, so the easy bit here is what's the sign? It's well, okay, first off, positive or negative, right? Okay, so it's positive, and so the convention that we'll use was just like with integers, that a leading one indicated that the number was negative. And so, like that, we'll just, I mean, it worked there, so we'll just keep the pattern. A sign bit of a 0 indicates that your number is not negative, which is to say, unless it's 0, that means the number is positive, okay? And a sign bit of a 1 will indicate that the number is negative. And that's just the convention we use. We didn't have to choose it that way, but that's, like I said, that's the standard. So um, to some extent, you're not allowed to argue with it. You're about to argue. No. Uh-huh. Sort of. For right here, I wouldn't write it that way. I would actually write a negative sign. Okay. Because what I'm doing is first writing things just sort of on paper for human consumption, and we'll worry about the encoding in a second. The reason I wouldn't have written it 11.01 right there is because I wouldn't want you to think that that was 3 point something, okay? But also, um, yeah, okay. So there will be another one in a moment, or we'll say if the number was negative. Um, but yeah, we'll worry about the. So I'm trying to do this sort of in two pieces, right? We've got the piece where we need to just figure out how to write this as a human, and then the second piece, which is to actually encode it for computer consumption. Okay, okay, and we'll sort of layer this together. All right, so I'm going to do the Mantissa next. Um, the Mantissa is everything that follows after the radix once you've got it in normalized form. Okay. Um, okay. So the encoding that we'll use for this will allow us 4 bits for our Mantissa. And because we have a normalized number, the the thing that's right before the radix is a 1, and we know it's a 1. So we don't have to encode that because it's always a 1. Okay, so if I'm going to use 4 bits for the Mantissa, what is the Mantissa in this case? What follows the radix? 0, 1. Well, I just said 4 bits. What are the other 2 bits there for? 0, 0. Okay, so my Mantissa is that. And this corresponds to that. If we had more things after the radix, they would be included in the Mantissa. Okay, now we'll talk about a problem in a moment there. But all I'm doing is I'm taking the bit pattern as it appears. Okay, so just whatever the bits are, and I'm going to have precisely 4 of them. And if some of them need to be sort of silly zeros at the end, then there'll be silly zeros at the end, and that's that. Okay, is that okay? Yeah. Okay. And again, why don't I have to include that 1 that's before the radix? It's always a 1. So there's no need to bother encoding it because what else would it be? It's not going to be a 0. Um, because if it were a 0, that would indicate a denormalized number or that we have the number 0. Ah, well, then I would write that as 1 times 2 to the minus first, right? Oh, because, okay, I see. Yeah. And so then the first thing is a 1. right? So I'm allowed to use negative exponents, and that's how you get out of that trap. Okay, in the same way that what was the universal gravitational constant that we used last time as an example? We just scroll back to it. Um, this thing, 6.6 times 10 to the minus 11, right? That really, if you write it, is like 0.00000 blah, 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 right? But you can shift everything so that it's 6 point something, and then, all right, it's got a negative exponent. Um, in this case, what the number we're working with has a positive exponent, but we can always do that as long as the number's not just flat out 0. And if the number's flat out 0, well, we kind of should know what we have in front of us, right? That's sort of a special number. Okay. Good. So the exponent is the fun one. Oops. What is the exponent in this case? It's the number 1. Okay. That's not so bad, hopefully. Sorry, I just need to pull up one thing here real quick. Let's see. CSC101, spring 20, is it in here? Here we go. Okay. So the exponent is the field or the part of this that's going to be the trickiest, okay, for reasons that will become hopefully more clear in a minute. What is the exponent just as a number for this particular example? It's the number 1. Great. How we encode that is the funny part, okay? So if I were to, I've got to decide how many bits I'm going to allocate to encode my exponent, okay? And the standard that I'm going to use is 3 bits. Okay, now why did I come up with the number 3? Well, if I have 8 bits total, I need to spend 1 on the sign, 4 on the mantissa. Well, that leaves 3 left over, right, for the exponent, okay? And if we do this with 16 or 32 or whatever, the split between the different parts is a little different, but that's basically the idea here. Okay. All right, so I'm going to encode this in 3 bits. Now, if I write the number 1, okay, so step 1, um, the exponent that we had was the number 1. No matter what exponent I get, I'm going to do what's called biasing it. And I'm going to subtract 3 from it. Okay? Actually, hang on one second. I've got this backwards. Hold on. Okay, so depending on which direction you're going, you have to either subtract or add, and I have it backwards. Okay, so the exponent is the number 1, right? How would I encode the number 1 using 3 bits? 0, 0, 1. Okay, big shock there, right? That's not what I'm going to encode. I'm going to encode 3 bigger than that. Okay, now you might say, why, Dr. McKinney? That's insane. Okay. The reason that we're going to do this is it's going to make, well, it will solve 2 problems. Okay, one, it means that we don't have to think about the exponent as being in 2's complement. Okay, which is good. That makes things a little easier to compute. The other reason is that it will make it very obvious to tell whether or not a number is so if I have two floating point numbers and I want to know which one's bigger, it makes it really easy to determine that if you throw in this bias. Okay, so all this to say is that the field looks 3 bigger than it is. Okay, so 1 would be 0, 0, 1. Okay, and I'm going to make this thing look 3 bigger than it actually is. Okay, what's 3 in binary? 1, 1. Well, yeah, it depends on which order you start or which end you start with. Okay, but it would be that number, right? So the top number 0, 0, 1 is our exponent, and the second number is the number 3. Okay, which is my bias. So if I add those together, I end up with this bit pattern. Looks like 4 counts as 1, okay, because of this bias of 3. Okay, so this is why the exponent is the annoying part of this, because of that bias. Okay, now, the bias is always 3 for an 8-bit number. It's different for a 16-bit or 32-bit or 64-bit number, but it's always the same number for those given sizes. So the 16-bit numbers have their bias, 32-bit ones have their bias, and 64 has its bias, and it's always the same for a given bit length. Okay, it's only the number 3 in the 8-bit case. It's different in the other ones. Okay, all right, is that okay for now? Okay, so finally, we encode the thing as an 8-bit binary object. Okay, and the order that we put these things in is sign bit first, then the exponent field, then the mantissa field. Okay, and that again is a standard, so we just stick with it. Okay, so what was my sign bit for this particular problem? All right, so sign bit was a 1, exponent field was what? Okay, that was the, looks like 4, but really counts as one thing, right? The exponent's the funny one. Okay, and finally, what was my mantissa? 0, 1, 0, 0. Yes, for 8 bits. Yeah. Okay, so that is our encoded binary number. This is what 2.5 would look like as an 8-bit floating point number. Okay. Oh, to interpret that as an integer?
Yeah, like as a note.
It doesn't, right? So, no, fair point. So the question is, how does a computer know to take this as a floating point number as opposed to an integer? And the answer is it doesn't. Okay? It's just a bit pattern to the computer. It's how you manipulate it where you have to know which thing it is. Okay, so when you write a program to do something with this number, you have to say, okay, like computer, I want you to add these two numbers together, but I want you to add them as a floating point numbers. And that circuitry does its thing and spits out the answer, right? So the computer isn't psychic. It only knows how to interpret the data if you tell it by means of an instruction, which gets encoded somewhat separately. We'll talk a lot about that later towards the end of the semester. Yes. Oh yeah, I'm an idiot. Thank you, guys. The number was positive. Sorry. Yeah, the one for the sign bit would be if this were negative 2.5. Okay, and excuse me, that actually is really nice because it means that if you want to negate a floating point number, all you got to do is just flop the far left bit. That's it. Okay, now with integers, how did you have to do that? How did you negate an integer? Yeah, you had to flip all the bits and then add one. Okay, so the procedure for negating integers was a little bit of a pain. The procedure for negating floating point numbers is actually pretty easy. You just flop that far left bit and that's it. Okay, that's nice. Uh, okay, so let me give you guys a minute to finish scribbling that down and try and digest it, and then we'll look at some more examples. Because look, I know this floating point stuff is annoying. All right, now there's one other minor annoyance about it. So the book, if you look up the floating point section in the textbook, guess what? It's there. Well, sort of. I mean, at this point, I think the next time I teach this class, there won't be a book because I've written enough notes and stuff now that there's no need to have one. Um, and eventually, I'm just going to sit down and write my own bloody book. Okay, because you know what I have found in my life as a teacher is that I am never happy with any textbook. There's always something I don't like about it. Okay, so hang on one second. Um, if you look at the floating point section in the book, it's wrong. Okay, or let me clarify what I mean by wrong. So, you know how we've got this hidden one that we can assume is there because of how scientific notation would have to work in binary? He doesn't assume that. He actually encodes that one. Okay, and so it his standard, the way he's done it, it works, but it works differently than the true floating point standard that is described in IEEE 754. Okay, so a few years ago, I was like, okay, this is silly. I'm going to rewrite that section basically to follow the standard from the how 16, 32, and 64-bit work so that when I'm teaching 8-bit in this class and 64-bit in the architecture class, it's the same thing, okay, just with more bits. Okay, so because of that, that section of the book is not quite right. I've got some notes on this that I've written, and I need to keep adding things to them, to Canvas I shall post them. Okay. Yes, Mr. Runge. Okay. So first off, let's make sure that we understand that the exponent is the number 1. Okay. And that's just like, is that part okay? Okay, good. So we know the exponent as a number, a base 10 number for us as humans. Okay, good. Then the question is, how do you encode that thing? Okay, and if I wanted to encode the number 1 on a computer or in binary, I would write it like so. Okay, so that's the actual numerical value of the exponent, but that's not what I put in the exponent field. The exponent field looks looks 3 bigger than it is. Okay, and that 3 bigger is called the bias. So I take the exponent just written down in binary, and I'm going to add the bias to it. Add 3, and I got 4, or the bit pattern 100. Okay, and that's what I'm going to put in the exponent field, is the thing that looks bigger than it really is. Okay, and yes, I know that's annoying. It's if we're going the other way, right? So if I gave you this bit well, you can't see it because it's cut off here. So it depends on which direction you're going, right? And we'll do both of these, right? So here I started with the number 2.5, the base 10 number, and I said, let's encode that in binary. What about if I had made up another bit pattern and said, decode this bit pattern, what does it stand for? Then you would subtract the bias because you're going the other direction. Okay. Huh? Yeah. No. Perfect question. Right. And we will do that. Right. Um, I'll give you a number and say what's the bit pattern that encodes it, and same thing the other direction. Here's a bit pattern. Figure out what it means. Okay. Good. Yes.
For the Mantissa, this would be, so it goes 1/2, 1/4, right?
Yes. And then 1/16, 1/8. Or well, okay, so let's go back up to here, right? So the first thing I did was where I've got the 0, 1 in the top red box, right? Okay, so if I were to decode this, this would mean 1.25, right? Because a quarter is 0.25, right? Yeah, okay. Times 2. Well, what's 1.25 times 2? Which is the number we started with, okay? So the Mantissa is just a 4-bit pattern. I had already written down 2 bits, the 0, 1, okay, but it needs to be 4 bits, and so I just tack on 2 extra zeros to make it 4 bits, okay? And if I had chosen a more gnarly number, like 2.75, then I would have also needed a 1 here. Okay, we'll look at more examples of this so it'll start to sink in a little bit more. Okay, because yeah, I know this is confusing, and it's 8 in the morning, and you guys aren't fully awake yet, so or 8:34 in the morning. Okay, so let's do 2 things here. The first is there was the little cool website that I showed you guys last time called Float Toy. This thing. Okay, so let me actually let me just type in 2.5 here, and it's going to encode this for me, right? Let me blow this up so you can see it a little bit better. But it's going to do it under the 16-bit standard, okay? And so what we've done, and this is, I really like how he's color coded this and written it, right? This is essentially what we wrote down, right? Sign bit, or this is a base 10 number, right? So if it were negative, this would be a -1, okay? So sign positive, good, no problems there. Exponent 1, Mantissa, bit pattern for 1.25. 0, 1, yeah, sorry. The first one, what is that? That's the hard-coded thing that we don't have to worry about. 0.25, what is that as a binary thing? 0, then a 1, and then however many zeros are necessary to fit it into the field. Okay, so look at the Mantissa field, which is the red stuff. 0, 1, and then what's all the stuff to the right of it? Just a bunch of zeros to fit it into the correct box. Okay, so like when we did this in 8 bits, we had 0, 1. We were going to put it into a box that could fit 4 bits, and so what do the last 2 bits have to be to make it fit in the box? Just 2 extra zeros. Okay, here it's what, 8 extra zeros, looks like? Okay, does that make sense? Sort of? All right, now, same thing with the exponent. It's biased. Okay, the bias for 16-bit exponent, I actually don't remember. So let me look that up for a second. Okay, so the bias on 16-bit is 15. Okay, and now you might ask, how did I come up with 3, 15, and so on? Well, 3, how many feet, hang on one second. Oh, yeah, okay, got it. How did I come up with the number 3 for the 8-bit bias? How many bits do I use for the exponent? 3, okay? Take 1 away from that. 2. What's 2 to the second? 4. Subtract 1. 3. There's your bias, okay? So how many bits am I using for the exponent in the 16-bit system? 5, okay? Take 1 away. 4. What's 2 to the 4th? 16. Take away 1. 15. So your bias in 16 bits is 15. All right, in 32 bits, how many digits or how many bits do we use for our exponent? Just count them up. 8. Take 1 away. What's 2 to the 7th? 128. Okay. What's 1 less than that? 127. So there's your bias. Okay. So that's the formula for how you figure out the bias based on the number of bits. Okay. Now, for our purposes, like on exams and stuff, I'm only ever going to really ask you guys stuff in 8 bits because that's sort of enough to write down on paper. 16, 32, 64, they work exactly the same way with the one exception that the bias is different and how many bits you use is different. Okay, but otherwise, it's the same shit. Maybe I shouldn't say that on Twitch. So, well, yeah, watch, I'll get in trouble for that, but not the radish joke from last time, right? So, yeah, well, it is funny, right? Yeah. Now, I don't think I mentioned this, but they used that as a punishment for infidelity. Okay, so yeah, it was happening. Well, okay, let's put it this way. There are 2 constants about people, specifically men, okay, throughout history, as to what they're interested in and what they do. So, yeah, I don't have to leave that one up to y'all's imagination. They cheat on each other, on people. So, yeah. Okay, so if I were to encode the number 2.5, so like let's look at this encoding here. Right, the Mantissa looks basically like we had before. It's just got some extra zeros at the end. Okay, and if the number 1 was our true exponent, to which we add a bias of 15, what does this look like to you? It looks like 1, 2, 4, 8, 16. but it's 15 bigger than it really is, so what does it count as? A 1. That makes sense, just like before. Okay, yeah. Cole, question? Ah, great question. Okay, the largest exponent that you can write, well, would be if I put all 1s here, right? Okay, whatever that is. Okay, so the question is, what happens if I put all 1s in my exponent? Okay, so if I write all 1s, oops, does help if I love this because you click it, okay? So what does the exponent look like? Looks like 31, but I have to subtract the 15 because of um, the bias, and so I get that the exponent actually counts as 16, even though it looks like 31. Uh, yeah, so, well, because we're working in 5 bits, the biggest number you could encode would be 2 to the 5th, which is 30, well, minus 1. 2 to the 16th is gigantic, right? Um, okay, the reason that it's got 2 to the 16 there is because the 16 is the exponent, right? But what does the exponent get stuck on top of? Well, it's an exponent, right? So it's got to be something to that power. Well, what's the something? 2, because we're doing everything in binary. Okay, now you might look at this and you might say, wait a minute, Dr. C, what's with this NaN business? Huh? Yeah. Okay, so what's NaN stand for? Huh? Not a number. So you just had to pick this one, Cole. There are some special floating point representations. Okay, and I was hoping to avoid talking about this today, but you you know I've got doubting Thomas over here. So you know, yeah. So the floating point standard actually has a couple of special representations, some of which are for denormalized numbers. The number 0 is technically a denormalized number, okay, but guess how you encode 0? Probably all zeros. That would be the sensible thing to do, right? Okay, but that's sort of a special exemption. There are also encodings for infinity, minus infinity, and 2 different kinds of not a number. And you might ask, why the heck would you need something like that? Well, it's actually kind of a good thing, right? Because what happens if you have a floating point computation unit and you tell it to do 1 divided by 0? What should it return? Some sort of error, okay? Now, the word error is not a number, okay? So it has to return a bit pattern, and the conventions are that it would return, in that case, it would return plus infinity, or maybe not a number, depends on the situation, okay? And so having an encoding for that is actually kind of nice if you think about making calculators and whatnot, okay? So yeah, so we'll talk about sort of the exceptions to the rules a little more in detail later. Okay, but let me just decrease that a little bit, right? Then this is the number, 40,960, but that's how I'm thinking of it, right? Positive sign, exponents whatever, mantisses whatever, and there we go, okay? Now, if I do the same thing in 32 bits, let me shrink-a-voo this. Okay. Notice that the pattern seems to be somewhat similar, right? What's the mantissa? 0, 1, followed by a crap ton of zeros to make it fit. Okay. Almost the same thing, right? What about the exponent? Yeah, okay, so how did I get that? Well, what's the exponent's true value? 1. Okay, but what does that look like?
I think
128. Yeah, okay, because the exponent, or the bias. Mm-hmm. Yeah, it's 8 spots, not 9. Okay, so the exponent looks like the number 128, but that's 2 bigger, or sorry, 127 bigger than its true value. The bias is 127. Okay, so the benefit to this of having the bias be sort of a specific formula is that notice how the exponent field looks visually similar to what it was a minute ago, right? It just has some extra zeros at the end. What this means is that if you have a 16-bit number and you want to convert it into a 32-bit number to work with, it's actually pretty easy to do that. You just tack on the necessary number of zeros in the exponent and mantissa fields, and that's that. Okay, so if you do what we call type conversions, which is you're, say, taking a thing that's stored in the machine as a 16-bit number and converting it into an equivalent 32-bit number that has the same value, it's pretty easy to do that. You're just tacking on some extra zeros in appropriate places, right? That's not that hard, okay? All right, let me refresh the page a minute and to start to talk about one of the problems that we're going to have, and this is inherent to floating point no matter how many bits you use. Okay, so Evan that coded this thing, that's his, he chose sort of the starting example to be the number pi in 16, 32, and 64 bits. Okay, well, that's great. Perfectly good example of a number. But what do you notice about the 16, 32, and 64-bit representations of pi? Okay, when it gets decoded back to base 10.
on the 32-bit, it rounds off.
Yeah, it rounds off at some point, right? So we got 3.1415927 in 32 bits, whereas in 64 bits, that really should be 265 and then a bunch of stuff. Okay, and another thing that we could notice is, well, what about what's going on in the 16-bit department? 3.141, it doesn't round up. Okay, so it's not so much a rounding thing because it didn't seem to do it didn't round the way you would expect in both situations. Okay, so here's really what the issue is. What's the most, like if I gave you the number pi and I said you may write down precisely 4 digits, no more, no fewer, what's the most accurate that you could have pi using just 4 digits? 3.141 or 142, I guess, right, if you rounded. Okay, but point being, it's not 3.1415926, blah, 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 right? So can you fully encode the number pi? No, doesn't matter how many bits you use, because pi is, what kind of number is pi? It's a very delicious number. Yeah, it's irrational, which means you can't write it as a ratio of 2 integers, but it's even worse than that. It's called transcendental. Okay, now that doesn't mean that it spends a year out at a cabin next to a lake in the woods in Massachusetts. Okay, please tell me you guys all get that joke. Mr. Runge, why was that funny? Pop quiz.
You can ask him. He seems bored.
Okay, yes, would you explain? Hmm. So Thoreau is who I was thinking of. Well, okay, Mr. Runge, let me give you a second attempt. Oh, okay. Well, have you played Fallout 4? Oh, well, never mind. Who's played Fallout 4? Have you found Walden Pond? Okay. Yeah. It's set in the Boston area, and Thoreau built a little cabin out in the woods, and yeah, and then wrote about it in his novel called Walden. Hmm? Basically, yes. When I read Walden, I was totally surprised what was there because I thought he like literally went out and was a hermit in a cabin by himself for an entire year. But no, he was like, I mean, half the book is uh, like, well, I raised a bunch of green beans and other things, and then I was able to sell them for this amount of profit at the market. And I'm like, this is not what it was not what I was expecting. Okay. All right. So just to kind of to polish off here, the point I want to illustrate, and we'll talk about this in spades next week, is that um, there is sort of an imprecision built into this, right? Because we are using a specific number of digits or bits, whatever. You cannot perfectly encode any number. Okay, so one of the things we'll talk about next time is how do you encode the number pi in 8 bits? And the answer might surprise you. And this being Indiana, the answer is really quite appropriate. Do you guys know about the Indiana Pi Bill? We'll talk about that Monday. Okay. All right. I'll quit the stream. Have a fantastic weekend. Um, don't go to any crazy parties. Of course, you can't go to the cactus. Rip. Exactly. You can go like have a candlelight vigil outside the carcass of the cactus. Money. So